Good morning, everyone. Delores Knipp here. I'm using just a little bit of time to thank you for attending CEDAR and making this the vibrant meeting that it is. I see that the participant numbers are rapidly rising, so I'll wait just a moment to present the meeting particulars, which I think everyone is already familiar with. But this has been an exciting meeting, and although I'm so looking forward to getting back to in-person meetings, the opportunity to have participation from, so many other time zones and so many other countries and cultures is something that I think I'm going to miss a little bit, and we'll have to figure out in the future what kind of mix we want for CEDAR, because it's so enriching to have so many other participants than the ones who can usually afford to come in person. So I think I see the numbers reaching critical mass. I'm going to go ahead and remind you that the session is being recorded, and I think you have to click your consent for that. The Slido is being monitored by Shasha Zhao. And please enter your questions in Slido so that we can get those answered. And if they don't get answered, then they get transferred to Slack and handled there. Do upvote if you find questions that are really of interest to you. Everyone is muted upon entry, as and there will be times when someone is asking a specific question in the Slido sessions where we may unmute and ask you to bring in your camera. Finally, just a reminder for the speakers this morning, of whom there are 4 in our highlights and observatory sessions. You'll get a 2-minute warning from Astrid, and we'll have 2 minutes or so for answering Slido questions. And then after that, we'll transfer off to the Slack channel and discussion via email and Slack. So without further ado, I'm bringing up on a separate screen our presentations. So this morning we have 4 presentations: a science highlight by Yosuke Yamazaki, an early career highlight by Xuguang Cai. And then we have 15 minutes for poster awards for our students. There were some fantastic posters. They're going to be available online for a while, and Astrid will tell us a little bit later how long they're going to be generally available, but there's some fantastic material there. And then after that, Nathaniel Frissell will finish with the early career highlights. And to end the plenary session, we'll hear from Bob McCoy about this exciting new opportunities at HARP. So if we can transfer over to Yosuke Yamazaki, he's going to tell us about really important new science coming out of the coupling part of CEDAR, and talk about the quasi-6-day wave associated with sudden stratospheric warmings. So Yosuke, take it away.
Okay. All right. Hello, everyone. I'm Yosuke Yamazaki at GFZ Potsdam. This talk is going to focus on atmosphere-ionosphere coupling by the planetary wave called quasi-6-day wave. So in the past few years, we have made progress in understanding ionospheric effects by the quasi-6-day wave. And I'm going to show the overview of our recent work. First of all, I'd like to acknowledge my collaborators for their contributions, and I would also like to thank CEDAR Science Steering Committee for having me here today. Oops. Okay, so the story began a couple of years ago when I started to look at the equatorial electrojet, or EEJ, observations from CHAMP and SWARM satellites. These satellites operated in near sun-synchronous polar orbit. And each time the satellite flies over the dayside magnetic equator, the intensity of the equatorial electrojet is estimated using high precision magnetic data. So using CHAMP or SWARM data, we can make this type of plot showing the EEJ intensity as a function of longitude and time, practically at the fixed local time. And as we inspected a number of data samples like this, we noted that the EEJ intensity sometimes shows an oscillation with a period around 6 days. So in this example, the 6-day oscillation is clearly seen in the Pacific longitude sector here. And but in the African sector, there's only a hint of 6-day oscillation, and it's not nearly as clear as in the Pacific. Since we have the time series data from all longitudes, we can get the spectrum of the EEJ oscillation for different zonal wave numbers, like this plot. It shows that the dominant component has a period around 6 days and the zonal wave number 1. The lower panel shows a similar spectrum, but it is derived from geopotential height measurements from another satellite aura at a height of the lower thermosphere. So here we are comparing the wave signatures in the ionosphere and wave signatures in the neutral atmosphere. And there is a good agreement between the two, suggesting that the 6-day EEJ oscillation is probably due to wave forcing from the neutral atmosphere. So this 6-day oscillations in the neutral atmosphere propagating westward with zonal wave number 1 is quite well known as quasi 6-day wave. And is commonly observed in the mesosphere and lower thermosphere. Quasi 6-day wave is usually considered to be the Rossby normal mode 1-1 from classical wave theory, because the quasi 6-day wave shows a number of features similar to those predicted for the 1-1 mode. Since the Rossby normal mode itself is known for many decades, a number of studies investigated its potential impact on the ionosphere, and some studies go back to 1970s. Early studies often involved point measurements from the ground and the time and spectrum analysis of time series. More recently, much advanced studies have become possible because of the global data from both neutral atmosphere and ionosphere. And in this context, I'm going to show a couple of selected results from our work. Here we are comparing the quasi 6-day wave signatures in the neutral atmosphere and ionosphere. The blue line shows the quasi 6-day wave amplitude in geopotential height at 96 kilometers in the lower thermosphere as derived from aura MLS observations. The red line shows the corresponding amplitude in total electron content at low latitudes in the afternoon sector. And there is a remarkable agreement between the two parameters, although they are completely independent measurements, meaning that whenever there is a strong quasi 6-day wave in the neutral atmosphere, there is an enhanced wave signatures in the ionosphere. This goes from the year 2006 to 2011, when solar flux was relatively low. And this goes from 2012 to 2017, when the solar flux was relatively high. So during both solar minimum and solar maximum, the quasi 6-day wave can drive 6-day TEC oscillations. and its magnitude is up to about 10 to 15% of the zonal mean TEC. We have also investigated the quasi-6-day wave impact on the evening ionosphere. In particular, we looked at the pre-reversal enhancement of the equatorial vertical plasma drift. Since PRE observations are very limited, we used the idealized simulation from NCAR TIGCM model. So we conducted a wave analysis using the simulated PRE data. And the right panel shows the amplitude spectra of zonal wave number 1 component. The upper panel is for equatorial zonal wind at a height of the TIGCM lower boundary, about 97 kilometers. So it shows the amplitude as a function of day of year and period. The lower panel is for PRE equatorial vertical plasma drift velocity at a height of the F region ionosphere. PRE shows enhanced 6-day oscillations. The magnitude is about 4 meters per second in this example, when there is a quasi-6-day wave in the neutral atmosphere, suggesting that the quasi-6-day wave is an effective source of 6-day oscillations in PRE. This might have a broader impact on other evening ionospheric phenomena, such as equatorial plasma bubbles, which would be an interesting topic to study in coming solar maximum. So now we are going to look at the exceptionally strong quasi-6-day wave observed during September 2019 Antarctic Southern Stratospheric Warming, or SSW. This quasi-6-day wave event was also highlighted in the very nice presentation by Dr. Xuguang Cai on Monday. In the general context, the traveling planetary waves in the mesosphere and the lower thermosphere is sometimes observed to have a large amplitude during SSW events in the northern hemisphere. This is just one of the examples, and showing the large quasi-10-day wave in this case, following the final warming in March 2016. Compared to the northern hemisphere, SSW in the southern hemisphere are very rare. In September 2019, there was a southern hemisphere SSW, providing a great opportunity to investigate whole atmosphere coupling under Antarctic SSW. The upper panel shows a large temperature perturbation in Antarctic stratosphere associated with this SSW. The event was accompanied by a very strong quasi-6-day wave in the mesosphere and lower thermosphere. The amplitude was much larger than what was expected from seasonal climatology. Here we show the latitude versus height structure of the quasi-6-day wave amplitude in geopotential height during September 2019, as observed by Aura MLS and simulated by the whole atmosphere model Gaia. For this simulation, the troposphere and lower part of the stratosphere of the Gaia was constrained with the meteorological reanalysis data. By doing so, the Gaia is able to reproduce quasi-6-day wave response in the mesosphere and lower thermosphere. According to Gaia, zonal wind amplitude of this quasi-6-day wave exceeds 20 meters per second in the equatorial dynamo region, which is which is pretty large for this wave. So during this time, the swarm satellite detected a very large 6-day oscillation in the equatorial electrojet intensity around the noon local time. This figure shows the EEJ intensity as a function of longitude and time during September 2019. This is original data, and this is bandpass filtered data. So the 6-day oscillations are basically seen at all longitudes. Swarm satellites also detected the similar 6-day oscillations in electron densities and topside total electron content over low latitudes. These 6-day density oscillations are probably due to the modulation of the equatorial plasma fountain by the dynamo electric field. Here we compare the 6-day EEJ oscillation during September 2019 as observed by swarm satellite and simulated by the Gaia model. Gaia model is able to reproduce the 6-day EEJ oscillation with the correct magnitude. It is important to note here that the model assumed constant solar and magnetospheric forcing. So these variations are due to the forcing from the neutral atmosphere. About the mechanism, quasi-6-day wave can affect the ionosphere either directly by propagation or indirectly by modulating atmospheric tides. The nonlinear interaction between quasi-6-day wave and tides generates secondary waves that can contribute 6-day oscillations in the ionosphere. Our numerical experiments suggest that the secondary waves due to the quasi-6-day wave tide nonlinear interaction are the main drivers of the 6-day EEJ oscillation in September 2019. These panels show 6-day EEJ oscillations from our numerical experiments. In the left panel, forcing by the quasi-6-day wave was excluded from the model, while keeping the forcing by the secondary waves. In this case, we see a 6-day EEJ oscillations, just as in the original Gaia simulation. And on the other hand, in the right panel, we did the opposite thing. So this time we excluded forcing by the secondary waves while keeping the forcing by the quasi-6-day wave. And in this case, the 6-day EEJ oscillations are much reduced. So the results suggest that the secondary waves play a dominant role. The quasi-6-day wave tidal nonlinear interaction can generate a number of secondary waves. For example, the interaction between migrating diurnal tide and quasi-6-day wave leads to 29-hour standing oscillation and a 21-hour wave with zonal wave number 2. Similarly, the interaction between migrating semidiurnal tide and quasi-6-day wave leads to 13-hour wave with zonal wave number 1 and 11-hour wave with zonal wave number 3. And other secondary waves can also arise from the nonlinear interaction between quasi-6-day wave and other migrating tides and non-migrating tides. So our numerical simulation suggested that these secondary waves are important, but it didn't really say which waves are important.
2 more minutes.
Okay. Our analysis of global TEC data reveals the presence of some of these secondary waves. The most dominant ones are 29-hour standing oscillation and 13-hour wave with wave number 1 and 11-hour wave with wave number 3. So these components are the secondary waves due to the nonlinear interaction between quasi 6-day wave and migrating diurnal and semi-diurnal tides. And these secondary wave signatures are enhanced when the quasi 6-day wave itself is enhanced. So here is a summary of the main points of this presentation. The quasi 6-day wave can have a significant impact on the ionosphere. We have demonstrated that using global measurements from both neutral atmosphere and ionosphere. The quasi 6-day waves the quasi 6-day wave effects can be found in the equatorial electrojet intensity and the dayside plasma density at low latitudes. And the TIGCM simulation suggests that the quasi 6-day waves are also effective in driving 6-day variations in the pluriversal enhancement of the equatorial particle plasma drift velocity. We also showed that the exceptionally strong quasi 6-day wave during September 2019 Antarctic sudden stratospheric warming event. Gaia model reproduces this quasi 6-day wave and ionospheric response very well. Our numerical experiment suggests that the ionospheric response is not due to the direct propagation of quasi 6-day wave into the ionosphere, but due to the modulation of tides by the quasi 6-day wave. We have also observed the secondary wave signatures associated with the nonlinear interaction between quasi 6-day wave and migrating diurnal and semi-diurnal tides in the ionosphere. That's all about. Thank you very much for your attention.
Yosuke, thank you very much for this really concise presentation. We have a couple of questions in Slido. I think you might be able to see them, but I'll go ahead and read the first one off. It's the seasonal variation of the quasi 6-day wave zonal wind amplitudes that you showed resemble that of DE3. Are there any known connections between these two waves?
Zonal wind amplitude. The two phenomena, I mean, the quasi 6-day wave and DE3 are probably not directly connected. But what I know is the nonlinear interaction can occur between quasi 6-day wave and DE3. And in our study, we detected secondary wave signatures associated with the quasi 6-day wave DE3 nonlinear interaction. Both waves could come from tropospheric convection, so that it might be interesting to look at their connection.
Is that a numerical experiment that you can perform?
Yes, but usually to reproduce these waves, you need to include meteorological data. So it's probably difficult to determine the mechanism because waves are really coming from the data rather than generated in the model.
Okay. The second question has to do with your Gaia amplitude plot, and it asks, why is there another quasi 6-day wave amplitude growth in the thermosphere?
Okay, I understand what that means. One explanation is, so I showed that tides and quasi 6-day wave generate secondary waves. And one possible explanation is these secondary waves can again interact with tides that will produce the quasi 6-day wave again. That way the wave signatures can propagate into the thermosphere. I don't think that's exclusive explanation, but yeah, that should be contributing what we saw in the Gaia results.
All right. Thank you. If there are other questions, I think the discussion could continue on chat. I can anticipate that there was a lot to unpack here, and so there may be questions. I was thinking about them as I was going in, but not typing. So let us move to our early career science highlight given by Xuguang Cai from NCAR. He's also going to be talking about some unexpected responses or finding the response of the thermospheric composition to low to moderate geomagnetic activity. Are we connected? There he is.
Okay, I will share my screen. Okay, so can you see my share the screen?
Yes.
Okay, so hello everyone, my name is Xuguang and my topic is the new findings of the response of the thermospheric composition to the low and moderate geomagnetic activities. And before I proceed, I have to thank the CEDAR community to give me these opportunities. So first, let's see the motivation. So in Burns 2004, they found that for the thermospheric composition in the F2 region, therefore their responses to a same magnitude of a geomagnetic storm, the weaker background in the solar mean can lead to a stronger response to the geomagnetic forcing. So as you can see in these two figures, the N2 relatively changes during the storm are relatively larger in the solar mean. So then Burns' work arises on another question. So does the neutral composition in the thermosphere also respond to the weak geomagnetic activity during the solar mean? So here, with the 2D images of the thermospheric column density ratio of the O2 N2 provided by the GOAT, we can utilize this valuable data to investigate this question. So the 2D images of the O2 N2 cover a large area in the same time range every day. And if you want to see more details, you can refer to the essays 2017 and the 2020 papers. So here, we pick the two consecutive quiet days with AE disturbance less than 250 NT and the daily average KP less than 1. Then from the third day, there are some geomagnetic disturbances, but they are weaker than storm. And then we calculate the corresponding O2 N2 percentage difference. So here are the three cases we find in the 2019 in the May and the June. So as you can see, this top panel shows the AE and the KP, and all the AE's max are all the KP's max are less than 4, and especially for the case 2, the maximum KP is only 2.3, and all of the AE are less than 1,000. So then we first calculated the percentage difference of the O2 N2 between the first 2 quiet days, as it is shown in the second row. And as you can see, in the gold filled view, the longitude to the range is 120 west to the 30 east, and the latitude range is 5 south to the 70 north. So although there are some variations, but mostly they are not they are very weak and not the deviations. However, when we then calculate the percentage difference of the O2N2 between the disturbed and the quiet days, as you can see now all these three cases, they show a large area of the O2N2 depletions, and they are mainly caused by the geomagnetic disturbance. It should be noted that although here what I show is only a snapshot, but actually this kind of depletion in the gold observation, they all continues for more than 10 hours. And also they are in the daytime, so that means for the weak geomagnetic activity, the gold can observe the daytime, the observed O2N2 depletion can stay pretty long in the daytime sector. Okay, so then we also try to run the TIE-GCM with the Weimar as the high latitude forcing to see how the model reproduce, and we find that the model reproduce the case pretty well. And here we pick an example to compare. So as you can see here, this top panel shows the gold observed O2N2 percentage difference between the day 156 and the day 154, and there's a large area of the depletion, and with the time pass, it moved westward slowly. Then for the corresponding TIE-GCM in the same longitude and latitude range, it also reproduced a similar depletion region, and with the time pass, it moved westward slowly. So since the model can reproduce the observation pretty well, we can use the model to further investigate how the observed depletion is formed. So since the geomagnetic disturbance for the case 2 here is beginning around the 15 UT on the day 155, so we provide the temporal evolution of the O2N2, the percentage difference from the day 155 to the day 156. And as you can see, at the beginning of the geomagnetic disturbance, they are first formed the O2N2 depletion in the polar region due to the strong upwelling caused by the enhanced geo-heating. Then, with the time pass, the depletion region was moving equatorward, and also it correlated from the local in the night towards the local early morning, and finally, as you can see, at 10 past 6 UT, this depletion region was already in the mid-low latitude and then moved westward slowly, and then this one was what got observed after 2 to 3 hours. So as you can see, this whole process showing is pretty similar to the O2N2 response to the geomagnetic storm as summarized by the Delores 1980. So therefore, this work show that during the weak geomagnetic activity in the solar mean, the thermospheric O2N2 can have strong and long responses in the daytime. And if you would like to see more details, you can check my 2020 GIL paper. Okay, so then the above work raises another question. So what happens during the geomagnetically quiet time? Are there still compensation and ionospheric density disturbance? So here we make our rules stricter by setting the AE less than 250 NT for the whole day and the KP less than 2 to see what happened for the O2N2 and the total electron content. We pick the cases with 3 consecutive quiet days, and then we calculate the percentage difference between the third and the second day. The first quiet day is not used, so that the possible influence of the previous geomagnetic particularly of the previous geomagnetic activity can be avoided. So here, this first row shows the geomagnetic indices from the day 109 to the day 112. And as you can see, the AE are mostly less than 250, and the KP max is only 1.7. So this period is a very typical geomagnetic quiet period. However, when we calculate the O2N2 percentage difference and the TEC percentage difference between the day 111 and the day 110, as you can see here, they both exhibit a localized depletion region in almost the same longitude and the latitude range. And it should be noted that although what I show here is a snapshot at 10 past 15 UT, actually this kind of depletion continued for 10 hours from the 11 UT to 21 UT, and especially for the O2N2, it is always in the daytime. And then we also run the TI-GCM driven by the Weimar, and the simulated results also show same amplitude and almost the same range depletion. And furthermore, we also run the TI-GCM without the geomagnetic activities, and the resulted ON2 and the TC percentage difference are almost nothing. And so, furthermore, we also provide the temporal evolution of the O2N2 percentage difference before the OT that the gold captured this feature, and we find that they already have O2N2 depletion region in the beginning of the day at a mid-high latitude, and then it moved slightly equatorward and then westward slowly. And as you can see, for the overplotted wind difference at 160 kilometer, at first the wind difference overlap with the depletion region is the equatorward, and then after 8-10 UT, it changed to a very weak westward component. So from the evolution of this depletion region, we can also find that this process is also quite similar to the O2N2 response to the geomagnetic storm. And furthermore, as you can see, when we run the model without the geomagnetic activities, there's almost no variation. So therefore, we can say that so at least in this case, during the so-called geomagnetic quiet time, so sometimes the minor geomagnetic activity can still play important roles in the behavior of the O2N2 in the mid-high altitudes. And if you would like to see more details, you can check my 2020-21 GL paper. So in summary, first, the weak geomagnetic activity can generate a strong daytime response in the thermosphere O2N2, and with some maximum amplitude around 30% at mid and low altitude during the solar mean. Then during some geomagnetically quiet periods, the gold also observed a similar strong localized daytime O2N2 depletions, but it can also sustain for 10 hours at the mid altitude. And for the ionosphere TEC variation, it also shows a depletion in almost the same region of the O2N2 depletion. And finally, the model simulation are consistent with the observation and demonstrated that during some geomagnetic quiet periods, the observed O2 depletion can be caused by the minor geomagnetic activities. Thank you.
Thank you, Xuguang. Very interesting. It's something that I've always wondered about. Let's see what Slido brings up in terms of just fascinating to see what's going on even during the quiet times. So questions are showing up. How often does gold observe these O2N2 disturbances at mid-latitudes under the geomagnetic quiet conditions less than KP2 less than 2? Is that a regular occurrence?
Actually, this kind of observation is relatively less. Yeah, it's relatively less.
So they're rare.
Yes, they're rare. Since I did a rough statistical study, and from 2018 to 2020, I find around 50 periods for such geomagnetically quiet period, and we only find 7 to 8 periods with the apparent O2N2 day-to-day variations in the mid-latitudes.
So less than 25% of your intervals.
So,
okay.
Yeah.
The next question is what lower atmosphere forcing did you use in your quiet time TIEGCM simulations? And can the day-to-day variations in the tides and the planetary waves be responsible for what's observed in the gold?
Okay, yes, this is a very good question. Yeah, so for this kind of simulation, we just use the monthly tidal climatology. And as for the day-to-day variability of tides and the planetary waves, so for the tides, based on some previous studies, their main influence of the O2N2 in the low latitudes, while here our focus is in the mid and high latitudes. So tides cannot be a major driver. Furthermore, for the planetary waves, again, based on some previous studies, the planetary waves can only cause around 5 to 6% variation of the O2N2, but here our observation, the amplitude is around 20 to and even 30%. Yeah.
There's a related question that's down at the bottom that says, in your simulations without the geomagnetic activity, how is the high latitude convection pattern specified, or is it constant over time?
We just set a very low value for our CP, CCP, and the HP power. Yeah.
For hemispheric power and cross polar cap.
Yeah, it's pretty low. It's 0.1.
Okay. Yeah. All right. Here's a challenge question that says in slide 10, there's a strong enhancement in TEC at the lower latitudes, latitudes lower than the depletion region you mentioned, but this enhancement isn't showing up in your simulations. Do you know what the reason is for this discrepancy?
Oh, yeah, of course. Since, as I mentioned earlier, my simulation for the lower boundary, it does not include the tidal day-to-day variability. It only has the monthly climatology. So yes, so of course for the lower latitudes, it not reproduce this.
And one last question. It seems to be a question, a comment. Are these depletions very narrow in longitude?
No, their longitude length is around 30 to 40 degrees.
All right. Well, thank you for that enlightening talk. And now I have to admit that I need to go back and read some GRL papers that I haven't set eyes on. All right, we're going to switch modes for a little bit now to my favorite part of the CEDAR meeting, or at least one of my most favorite parts, and that is the poster prize announcements from the poster committee chairs. And I will freely admit I'm not sure who's going to be the first speaker on that. So Reed or Astrid, can you help me out? Or Julio, are you have it? All right, take it away, Julio.
Sure, thank you, Delores. Okay, can you share the presentation, please? Okay, great. Thank you so much. Good morning, everyone. And this is very exciting for me to announce these prizes. Just to provide some general overview on the 2021 CEDAR poster competition, some statistics and some numbers that are useful. So we have 136 posters that were presented this year overall, and 72 student posters in the competition. And we had 14 undergraduate students in this competition, which is fantastic. Students that we have were from various places, so it was quite a diverse group. We had students from the US, Brazil, China, Germany, Peru, Taiwan, India, and Iran. So the posters were partitioned in 3 days competition, and for each day, the poster winners were selected by our poster judges. So we thank all of the students presented a poster at CEDAR. The posters were amazing. So kudos to all of you for doing an amazing job in bringing high quality research for our community. So I'm pretty excited. Our community is very vibrant. See, with excellent presentations also from the student side. And I'm really excited. I learned so much by chairing this poster competition this year. Can we go to the next slide, please? So a special thanks, of course, to our judges. So we do appreciate very much the judges volunteering their time to look at this poster, helping us judge these posters. So I want to read each of them and please kudos to them for this amazing job. So Brian Harding, Xuguang Cai, Phil Richards, Lindsay Goodwin, Scott England, Megan Burley, Aramesh Saif, Chinju Zhu, Federico Gasperini, V. Selvaraj, Steve Kapler, Shantana Debochudur, Chihoku Kulens, Rafael Mesquita, Joshua Petit, Mac Jones, Luis Navarro, and Leslie Lamarche. And forgive me if I mispronounce your name, okay? We had also a committee for this poster competition. So I was chairing the committee this year. And in the committee, we have members from CEDAR Student Science Committee, Lin Qiang, Jens Overhigh, Asti Bat, Jonathan Snively, and of course, big thanks to Astrid Maute, who is always behind the scenes making all of this happen. So kudos to Astrid as well. If you didn't get a chance to be a judge this year, I encourage you to participate next year. It is an amazing experience. I have learned so much by participating in these discussions. I just want to point out that the poster judging committee from the CEDAR side, from the CEDAR CEC, didn't participate in the selection. We didn't vote in choosing the posters. We just facilitated the discussion. So we divided as 2 members were participating in day 1, 2 and day 2, and 2 and day 3 of each poster competition. So with that, I would like to also go to the next page that shows the criteria. So to be transparent, and also for the students to get their forms from round 1 and round 2, where you can get feedback about how your poster was viewed by the judges. So the criteria that we use for the selection of the winners this year, we had 2 members of the CEDAR CSCC that facilitated the discussion, as I said, but did not vote. Every poster received 2 scores in round 1 with 500 points maximum, and in round 2 with also 500 points maximum. These 2 scores were added. The judges discussed the scores and selected the best 8 posters out of this pool. The judges discussed these 8 posters further and finally make a selection of the first place in the competition out of this pool of 8 posters. Then they move into the best 7 posters where they discuss the second place. If an undergraduate poster made it to the top 8 and there was more than 1 undergraduate in the competition, an honorable mention was chosen as well. So this was the general criteria. And I want to share with our community that the judges spend a lot of time in selecting these posters. So that means that the poster quality, everyone that participated was incredible. So I'm going to read the poster winners from day 1, day 2, and day 3. And these posters are going to be displayed for 1 year on the information I provide at the end, and also in our CEDAR website that we all have access to. So can we go to the first prize on day 1, and will be second prize. Poster competition was awarded to Catherine Davidson from the University of Alabama, Huntsville. The title of the poster was Investigating Ionosphere-Thermosphere Coupling in the Night Side Aurora Alba. Congratulations to Catherine Davidson from University of Alabama for second prize in poster competition day 1. Next, we're going to announce first prize on day 1 that was awarded to Lance Davis from the University of New Hampshire. The title of the poster is Proving the Density Profile of the Thermosphere Using Lost Cone Measurements. Here the display of the poster. Congratulations to you, Lance Davis, for your accomplishments. So we can move next to day 2. In day 1, we didn't have undergraduate selection. In day 2, we have an honorable mention undergraduate poster, and it was awarded to Jasmine Aricoch from the Radio Observatory of Jicamarca, Instituto Geofísico del Perú, Lima, Peru. And the title of the poster was Modeling Ionograms with Deep Neural Networks, Applications to FOF2 Forecasting. Congratulations to Jasmine Aricoch for such a big accomplishment. Going to move to the next award, which is the second prize in day 2. The judges selected Jack Wang from the University of Colorado at Boulder, and the poster title is Numerical Study to Uncover the Driving Mechanism of the Migrating Diurnal Tide Day-to-Day Variability. Congratulations to Jack Wang for winning second prize in day 2 poster competition. Next, we have first prize and the second day of the poster competition, and the judges awarded this prize to Reza Janalizadeh from the Penn State University, and the title of his poster was, or is, Revisiting the associative detachment reaction of nitrogen molecules with the anion of atomic oxygen in the context of gas discharges. Congratulations to Reza for first prize poster competition in day 2. So we go next to day 3 with honorable mention for undergraduate student. The judges chose Alana Cardenas Othol from the University of Michigan, and the title of the poster is Statistical and Event Analysis of Phase and Amplitude Scintillations associated with polar cap patches. Congratulations to Alana for this award. Go next to second prize on day 3 of the competition, and the judges chose Harikrishnan Charuvil Ashokan from the Leibniz Institute of Atmospheric Physics in Rostock University, Kölnsburg, Germany. The title of the poster is Validation of Multistatic Meteor Analysis using Realistic Mesospheric Dynamics from UA Icon Model, Reliability of Gradients and Vertical Velocities. Congratulations to Harikrishnan for second prize on day 3 of the poster competition. The first prize on the third day of this poster competition was awarded by the judges to Clayton Cantrell from the University of Colorado Boulder, and the title of the poster is Deriving Column Integrated Thermospheric Temperature with the N2 Lehman Birch Hotfield 2,0 man. Congratulations to Clayton Cantrell for first prize. Kudos to all the winners. And the first prize winner this competition will receive an electronic copy of Understanding Space Weather and the Physics Behind It by our chair of CEDAR Student Science Committee, Delores Kopp, Professor Delores Kopp, which we thank for her amazing leadership in chairing CSCC. We also thank the Space Technology Series for making this possible. And finally, on the last slide, I'm sharing with you the QR code where the posters, the winning CEDAR posters, and all the posters at the CEDAR will be displayed. And also, as I announced at the beginning, the winners will be, the poster will be displayed for 1 year in our CEDAR main website. Congratulations to all the winners, and those of you who didn't win, you did an amazing job. The judges have a hard time trying to choose every day the best of the best. And one more time, thank you so much to our judges for their time. And I encourage those of you who couldn't participate this year in judging a poster to please volunteer your time to help in the poster selection next year. Thank you so much.
Julio, thank you so much for all of the efforts that you put into chairing this committee. I think this is such an important activity that supports our students, and without your leadership and the really hard efforts of all of the judges, I think this would not be possible. But most of all, thanks to the students for their amazing efforts, and congratulations to the winners. I look forward to digging into that QR code and looking much more deeply. So thanks again to everyone for helping our students initiate their participation in science. All right, and I'm seeing a lot of congratulations coming over on chat, so keep that up. We will now go to our second early career science highlight. given by Nathaniel Frissell at the University of Scranton. His title is Magnetosphere, Ionosphere, Atmosphere Coupling and the Building of an Amateur Radio Citizen Science Community. Please do take it away, Nathaniel.
Thank you so much, Delores. And thank you so much to the CEDAR Science Steering Committee for inviting me to give this talk. So today I'm going to talk about, as Delores said, atmospheric coupling and the building of an amateur radio citizen science community. And so here at CEDAR, we're very interested in the dynamics of atmospheric regions and how they couple together. The ionosphere is of particular interest to many of us. It's a region that links the neutral atmosphere and the magnetosphere. It has interesting physics in its own right, and it dramatically impacts many of the technological applications that we have, including radio communications and satellite navigation. And so we have a number of frontier topics that we've been talking about all week. And some of them we've even heard about today. Coupling from above versus below. We know that space weather drives the ionosphere from above, but we're also learning how important the terrestrial weather is from below in driving the ionosphere as well. Also looking at weather versus climate. We have some reasonable understanding of ionospheric climate, but we have so many open questions about ionospheric weather, that short-term variability. So how do we make progress? Well, I started doing this back when I was in graduate school with Mike Rahanomy and Joe Baker, and they had me looking at medium-scale traveling ionospheric disturbances seen in the mid-latitude superdarn radars and comparing them to the MSTIDs seen at the high latitude radars. And I did a significant amount of study on that, a statistical study using these 10 radars. And that's where he came up with this rather striking result that showed that the real strong correlation between the MSTIDs seen in the superdarn radars up here and how well they're correlated with the polar vortex index that we calculated. And so this really, and how not correlated it was with the auroral electrojet index and some of the other space weather indices. And this really drove home some of that, how we can start to investigate or continue to investigate this lower atmospheric ionospheric coupling and also the space weather coupling. So this is how where I started with superdarn. And then I started asking, well, how else can I look at these sorts of things? And really the thing that got me into space physics to begin with was amateur radio. And this is a hobby for radio enthusiasts, communicators, builders, and experimenters. And it's a very wide-reaching demographic of people. And one of the things that's very interesting about them is that they use the ionosphere on a regular basis to communicate. And this is really where my passion came from. And so if you look at how they communicate, there's a lot of similarities between how we sense the ionosphere with superdarn radars and how amateur radio operators communicate. You have the ionosphere here, and you can launch radio waves through it, and you get ionospheric refraction. If you have a transmitter here and a receiver here, if you see perturbations on the receiver, if you look at them correctly and make sure they're measured properly, you can map the variations in the received signal back to phenomena happening in the ionosphere. And while I was in graduate school, I had the good fortune of being able to help build the Adak Island superdarn radar, which unfortunately doesn't exist there anymore. But it was a really great trip, and that's where I got to meet Ethan Miller. And he's a fellow ham radio operator, and he introduced me to something called the Reverse Beacon Network. And this RBN is a global system for monitoring ham radio operators on the HF bands communicating back and forth using Morse code. And they would store all of that data in their central database. And I said, I wonder if I can use that to detect ionospheric disturbances. And so Delores asked me to write a paper, or I submitted a paper to Space Weather at a time that she was taking over editorship. And I was able to show that, in fact, yes, you could see the effects of a solar flare on this network. And there are more networks than just that. There's the WhisperNet network and the PSK Reporter network that all contribute to this global data set. And it's quasi-global, it's organic and community run by the amateur radio operators. And we actually have data back to 2008. And so you can see just a glimpse of that. This is just Reverse Beacon Network and WhisperNet for the last solar cycle and split among different frequencies. And we have the F10.7 up here. And you can see just very quickly the solar cycle effects and diurnal effects in these plots. Again, this is showing, these are showing the midpoints of communications between ham radio transmitters and receivers. And so, as I said, we can see solar flare effects. So this is looking at the ham radio communications in the European sector to the solar flares that took place on September 6th, 2017. And you can just see how these flares just totally black out the communications there. But that's not the only thing we can see. We also looked at what the solar eclipse in 2017 would do to the amateur radio communications. And so this is a figure from a GRL looking at the solar eclipse, the communications during the solar eclipse during 2017. And if you look at the 14 megahertz communications over here, you can see that there's lots of communications before the solar eclipse, and there's lots of communications after the solar eclipse, but there's very few in the middle as the ionosphere becomes less dense and these 14 megahertz signals escape out into space. But, you know, just looking at the radio communications themselves isn't quite enough. We need to do our best to link it back to physical phenomena and back to models to try and validate our understanding and learn new things. And so in that paper, I was also able to work with Joe Huba and a number of other people, Doug Drobe and my team, and we were able to get the outputs from an eclipsed version of the CME3 model. And we were able to demonstrate through ray tracing that the model matched very well with the amateur radio observations. And so now we have a way to start linking these communications to these physics-based models. Now, going back to my original work with SuperDARN in graduate school, I was wondering, can we see these traveling ionospheric disturbances in the amateur radio data as well, just that raw amateur radio data? And the answer is yes. So just within the last year or so, I've been able to take the amateur radio data from over the United States, and we could plot it this way. This is 12 hours of data, and this is distance between transmitter and receiver. And you can see oscillations in the skip distance here. This corresponds very well with a large-scale traveling ionospheric disturbance that would be moving across the entire continent. We can take this, we can line it up with SuperDARN observations from the Blackstone radar. This is beam 13, and you can see the skip distance in the SuperDARN observations matches the skip distance with the amateur radio data. So now we're starting to have a way of comparing these observations directly with these well-known space physics instruments. And we're able to use these to complement the data sets and have them fill each other in and inform each other where there might be missing gaps or of information, or we might be able to see new information. Similarly, we can look at GPS or GNSS total electron content for that day, and you can see the giant wave fronts that correspond with that signal, and it has the horizontal wavelengths and phase velocities consistent with the amateur radio data and consistent with a large-scale traveling ionospheric disturbance. So moving along with this, we can also do statistics similar to what I did with the SuperDARN data. And I've been having one of my undergraduate students, Diego Sanchez, do that. Just look at the occurrence statistics of the TIDs and the amateur radio data as a function of time. And we see the same sorts of seasonal variations that we saw in the SuperDARN data when I looked at that in graduate school. So we're starting to see ways to really connect these data sets together and to find similarities in the observations, and then potentially bridge out to new territory as well. So all of this came from the amateur radio community. And in a lot of ways, what I have shown you has been very much the amateur radio community providing passive data. They set up these networks, but then I take the data and I've been massaging it with my students and working on this. However, the amateur radio community is much, much more than that, because many of the people in the community are people who have advanced degrees and years of experience and distinguished careers. And there's also people in the amateur radio community who are young and are very interested in what we're doing in terms of ionospheric science and space science and how radio propagation works. And so if we could come up with a way of joining the amateurs with the professional community to share knowledge to each other's benefit, that would be really great. And so as we were coming up with for the 2017 eclipse, we were able to start the Ham Radio Sciences Investigation. And this is a collective that allows university researchers to collaborate with the amateur radio community in scientific investigations. And so we want to advance scientific research and understanding through the amateur radio activities, encourage the development of new technologies to support this research, and provide educational opportunities for the amateur radio community and the general public. I've had many great collaborators so far. You see Phil Erickson right in the middle of this picture, and there's Magda Moses and many other people that you might recognize have been participating in this. And so what are some of the benefits of amateur radio citizen science? It really gives us access to a broad expertise and different perspectives. People who listen to the signals don't just look at them on graphs. People who actually have to use these things to communicate. It gives us the ability to collect data on a large scale that can complement existing space science data sets. We now have the ability to do widespread outreach. We have a mechanism for reaching and involving youth in space science well before graduate school. We have a unique opportunity for community members with significant experience to mentor the younger generation. And this is something I've really benefited from. Many of the HamSci volunteers who are retired, they're able to come on to the Zoom telecons with my students and spend a lot of time with us, helping us and mentoring us. And it's just been a great collaboration. So one of the really nice things that's come out of this collaboration from one of these HamSci meetings that we've had is this personal space weather station project, which is currently in development, funded as a DAISY Track 1. And this is going to be a multi-instrument ground-based device designed to observe space weather effects, both as a single point measurement and as a part of a larger distributed network. And it's personal because it is being designed such that an individual should be able to purchase one and operate in their own backyard. But we're also designing it so it takes into the account the needs of not only the amateurs, but also the professional researchers. So there are many people in the professional community. I know we have got participation from Dartmouth and MIT Haystack and others who are interested in this once it becomes available. And this is a highly collaborative project again, and this shows once again the power of this amateur radio professional collaboration. Many of the logos you see on here are familiar to you because of the CEDAR community. But some of them, we've only gotten these collaborations because of the amateur radio connection. University of Alabama in Tuscaloosa and the Case Western people, they were brought into this collaboration through the amateur radio connections. And then the Tapper and Zephyr Engineering, this collaboration, many of whom of these people are volunteers, is strictly because of the amateur radio connection. So it's really been amazing. And we're able to develop two different tracks of this personal space weather station, a low cost one, which is geared more toward rapid deployment and easy availability towards schools and other hobbyists, and also the software defined radio version, which is going to be the more powerful tool that many of the professionals are looking at as well. And so perhaps the most important part, one of the most important slides that I have is the future work. And it's not just, what I've done as an early career highlight, but where I'm hoping to go. And I'm really hoping to tie all of this back to the science and asking the question, what are the causes of the ionospheric variability that we're observing? And so I currently have projects which are working to combine the amateur radio, dive back into the SuperDARN data sets, work with the GNSS data. I'm collaborating with other people using other data sources from the CEDAR community. And we're also working on doing more ray trace modeling and advancing that, putting it together in a meaningful way. I'm looking forward to developing the personal space weather station network to generate new measurement techniques and data that will help to resolve these problems, and work with other professionals here in this room, other students, other community members to help address this question. And then that's the science, but also I do have future work for our community together, again, driven by the question, how do we best foster the HamSci program so it truly does bring together the amateur and professional communities? How do we create opportunities for open, positive discussion, listen and respond to the needs of both communities, and find ways for people to participate that really match their interests and passions? And so with that, I'd like to, again, thank all of you for your time and for giving me this opportunity to speak.
Nathaniel, thank you so very much. Just to the general community, I was so impressed with Nathaniel when he was a graduate student. And as he mentioned, I did commission a paper from him, and I think it has, well, he has launched his own career, but certainly getting that information out there was critical. And I've been seeding the Slido with a couple of questions, although I don't see them showing up here, so must be.
I see them.
Oh, you see them. Oh, okay, fine. Oh, I bet they're just waiting to come in. Yeah, my questions can come a little bit later. It has to do with, power and cost requirements, some of which you've answered. But right now there is a question: what scale size TIDs can you detect with your ham radio data?
Well, I think it depends on the technique of the ham radio data that we're using. The technique that I showed you today, where we're using that large scale aggregate data, I'm really seeing the large scale traveling ionospheric disturbances, the ones that have wavelengths of, say, 1,000 kilometers.
Okay.
On the personal space weather station, where we're doing some of these Doppler techniques, we're still working on resolving the scale sizes, but I believe that's a much more sensitive approach, and we can see smaller scale ones.
Okay. And a new question, let's see. How do solar flares and geomagnetic storms affect your HF radio signals? Which one affects the radio signal more? I
mean, just from looking at the data, I would really say the solar flares do. It's a much more clear and easy to understand signature. When you see a solar flare, it is clear as day. You see a dropout in communications, and you see it come back up, easy to analyze. The geomagnetic storms are significantly more complicated.
Yeah, I recall that from your paper.
Yeah.
There's another question here. What's the best way for CEDAR scientists to become involved in science analysis from the HamSci network?
Oh, there's a number of ways. First, just go to the hamsci.org and click Get Involved. We have a Google group that you're encouraged to join. Through that Google group, we have during the academic year, we have bi-weekly research telecons where you can come on and present your work, whether it's ham radio or not. You'll be able to present it to the community, and then we'll be able to give you feedback how you might be able to get involved. We have an annual HamSci workshop, which we're hoping to have in person in March at the University of Scranton. So I'd encourage you to come submit an abstract to that. And you can also just email me, and we can discuss some ideas.
Okay. And I just wanted to ask one additional question. It has to do with the cleanliness of power and that kind of thing. I noticed on many of your maps that there was not a lot of signal showing up from, say, Africa or in Central or South America. What does it? What are the requirements? You mentioned the cost. It's pretty low, but what are the power requirements for such a station?
Oh, the power requirements are really very modest. I'm sitting in front of one right now. You can just use a standard home 15 amp, 120 volt, power outlet to power your station. In fact, this week and starting tomorrow, there's something called Field Day where hams will go out into the field and they'll be running off of solar power and
Wow.
12-volt batteries and things like that. So it can be very modest.
Okay, so that really does open up the opportunity for participation in places that have often not
Absolutely.
had the ability to maintain or sustain power.
Yeah, and
really clean
if you're
power.
just receiving, the requirements are even less.
Okay. All right. Let's see. Just one last question, and I think
Sure.
I know the answer to this. How often do flares affect radio propagation?
You know, fairly regularly.
Yeah. All you need is a flare, right?
Yeah, you just need a flare. And actually, I think what's really interesting isn't just, you know, when you see the blackouts, that's one thing, but even a C-class flare can affect the Doppler shift that you see in our received signals. There was one right in the middle of the eclipse that just kind of puzzled us, and it's just a small C-class flare, and that would
Wow.
actually affect the Doppler shift. That was
All right.
fascinating.
Thank you.
Thank you.
Thanks so much, Nathaniel.
Thanks,
All
Delores.
right, we will move to our final speaker in plenary session. That's going to be Bob McCoy talking to us and telling us about the new opportunities in HAARP for subaraural science. So I will mute myself and take it away, Bob.
Thanks, Delores, and thanks CEDAR Steering Committee for this opportunity. Can you see my screen?
Yes.
Good.
Let's see, you are in there. If you can go, there you go. There you go.
Bob, could you
So-
hit swap displays? Thank you.
How's that?
No. Yes.
Okay. Thanks, everybody. Thanks to the National Science Foundation, we're expanding our activity at the HAARP facility, and we're trying to create a subaraural geophysical observatory. As you know, the Department of Defense, Navy, Air Force, and DARPA built HAARP about 15 years ago. And in 2015 or 2012, the Air Force decided they didn't want it anymore. So in 2015, they gave it to the University of Alaska Fairbanks. It took us about 1.5 years to get it out of mothballs up operating. And we've been operating ever since. We just completed our 7th campaign this morning at 6:30 Alaska time. Jessica Matthews, who's the HAARP manager. This talk is myself, Jessica Matthews, and also Dave Heisel, who's part of a HAARP advisory committee. I'll talk about that more later. HAARP is a very exquisite facility, the most powerful and exquisite of its kind in the world. 33-acre array of HF transmitters powered by 5 4,000 horsepower diesel engines. They can generate 12 megawatts, and we can transmit 3.6 megawatts, anywhere in the range from 2.8 to 10 megahertz. This is a photograph. This is a video of the 5 diesel generators running. It's pretty loud in there. You need hearing protection, but you can see how big they are. You can only run 4 of them, and when 4 of them are running, we're burning about 820 gallons of diesel an hour. So it's a very, very powerful facility. There's on the antenna field, there's 30 trailers full of electronics with transmitters and circuits. Here's the inside of one on the left, and on the right, the antennas. Because these were built on permafrost, the Air Force put thermosiphons on every one of them to make sure they stay, as the permafrost thaws and sinks, that they stay vertical, and they've done a very good job. So what HAARP can do, it's basically a large ham radio. You just heard about that. A lot of experiments. On the left is a laundry list of some of the things it can do: create ducts, air glow, generate waves. Often it's been used to use the ionosphere as an antenna to generate ULF, ELF, VLF waves that propagate up into the magnetosphere or get trapped in the Earth ionosphere waveguide. We can create multiple beams. We can transmit at any frequency and even move the beams fairly rapidly. Mike McCarrick recently figured out a way to lower the elevation down to about 5 degrees above the horizon. So we've got quite a bit of capability with HAARP. In 2013, there were a couple NS National Research Council publications. One, a decadal study. They talked about the importance of these active ionospheric facilities. And that in 2012, 2013, the NRC carried out a workshop. And that workshop highlighted in about 70 pages all the cool science that can be done with a facility like HAARP or with HAARP. now and in the future. At the bottom of this page is a link to that report if you want it. Quite a bit of science that can be done. That actually encouraged us, and we negotiated with the Air Force to take, based on that report, to take ownership of the facility. One of the figures in that report is a comparison of the 4 active ionospheric facilities. Arecibo is having some difficulty at the moment, but this shows that HAARP has much higher frequency range and power. This is a log scale than the other 3 facilities in the world, and can access science thresholds that the other ones can't. So this will be a part of an overall program we have at the Geophysical Institute to study the ionosphere. Here's a quick chart showing all sky cameras. This is a chart Mark Conti put together, showing LiDARs, all sky cameras, GPS receivers. This is to support rocket launches from Poker Flat North out to the Brooks Range or into the Arctic Ocean. It also shows the Pfizer Incoherent Scatter Radar and the SuperDawn radar scattered around the 3 of them in Alaska. This is an important part of it. And HAARP is located in Gakona, GAK. HAARP is at right about an L equals 5, which is a great location for sending signals deep into the magnetosphere. But we're saying subaurora because for the most part, Poker Flat is pretty much under the aurora quite frequently, but HAARP a little bit lower doesn't often have overhead aurora. So that means it has it frequently enough, but not all the time. So that means we can do experiments in a quiet ionosphere and also a disturbed ionosphere. Here's a laundry list of the current ionospheric diagnostics at HAARP, quite a bit of stuff. Not all ionospheric, we're talking about a geophysical observatory. If you're interested in having an instrument installed there, talk to Jessica Matthews, the HAARP manager. She can help you get it installed. And if it doesn't take much time or money to operate it, we can do that fairly easily. There's quite a bit of instruments there and also at Poker. Including one of the instruments there is the Muir radar. It was funded by Office of Naval Research. It's not totally functional now. About half of these transmitters are working, but we're talking to SRI. They're coming up this summer to take a look at this and see what could be done to get the Muir radar back working. It looks sort of like the mini Pfizer. It's 16 panels of what you have at Pfizer and Riser. So this would be an important capability to have operational. Mark Conti has a scanning Doppler interferometer. Right now it's up at Toolik Lake. He's going to be bringing that back to the GI, refurbishing it and bringing it down, installing it at HAARP. It has an all sky camera. It can measure winds and temperatures. It's quite a capable instrument, and that'll be operational at HAARP sometime soon. Here's some past science experiments. One of the nice things about HAARP is you can flip a switch and turn on geophysical phenomena. We take an overhead section of the sky, maybe 100 kilometers square, but instead of waiting for things like scintillation, you can actually cause scintillation. So the top half of the figure shows some data from Paul Bristow a few years ago, where he was turning on and off HAARP, creating scintillation, and then looking at the decay of that with SuperDawn radar. The bottom is a chart from Paul Bernhardt at NRL, showing he was communicating with a TACSAT-4 UHF satellite, flipped the switch, turned on HAARP, and created 20 dB fades at UHF frequencies. So it's a way to not just wait for the phenomena, but actually to cause the phenomena. Here's a chart from Chris Fallon at Air Force Research Lab, showing on the left the artificial aurora. We can create, this is a red line, we can create artificial aurora. But Chris was also modulating his signal with slow scan TV. So ham operators around the world can pick up the signals. They get excited and send back the imagery that he was sending out. It shows the power of this very powerful ham radio. Another chart from Paul Bernhardt showing the how HAARP has enough power to create its own reflecting layer. Some of these charts show 3 hours, but I think I understand he's shown that it can be up to 6 hours. So even in a disturbed ionosphere, there's ways to take a 100-kilometer patch overhead and make a shining layer that we can then use for other experiments. If you like Steve, here's some charts. Here's some sky imagery from Don Hampton last year, showing the Steve aurora over near HAARP. It's a great location. Again, being subauroral, this is a great place to observe this phenomena. So we wrote a proposal to the National Science Foundation. There's 6 of us in the science team: myself, Peter Delamere, Amani Reddy, Mark Conde, Don Hampton, and Vika Sunwalker. We're part of the science team. We have 5 years of funding to make HARP available to the NSF community. We have a HARP advisory committee headed by Dave Heisel, but it also has Jade Morton, Mark Olkowski, Wayne Scales, James Sheeran, Bill Bristow, Paul Bernhardt, and William Reeve. This committee will be coordinating campaigns and awarding hours. We're still struggling. We're still working with getting this up and running. We hope to do something like what was done at Arecibo. So stay tuned. There'll be announcements and a website that you can go on and request hours at HARP. Also, recently, Bill Bristow, Rich Collins, and Jintai Lee received funding from NSF to build a LiDAR at HARP. They're going to build a solid state 372 nanometer ion laser at Poker with the other 3 lasers there, co-located, get it working, and then transport it down to HARP. So we'll have that capability. Here's a list of some of the things that could be done. The nice thing is be able to do D region electron densities and also do LiDAR. So that'll be at HARP. We're also going to be reviving the PARS, Polar Astronomy and Radio Science. This is a great school. We was held a number of summers. Students come out, they spend some time at the Geophysical Institute in classes, go out to Poker Flat Research Range, go down to Valdez, and then come back to HARP, and students with their advisors carry out experiments. It's been a great feeder for the community. A lot of people in this active ionospheric community got their start at PARS. We're struggling to get it up this year, probably won't make it this summer, but next summer we'll have a PARS summer school, and we encourage you to apply for that. Stay tuned. And just to finish up, these are some, like I said, we finished a campaign this morning at 0630. These are some photographs from a couple of days ago showing the antenna array. It's an exquisite facility. It's in terrific shape. It's extremely powerful and very capable. We have a large area for ionospheric diagnostics, optical, radio. You can see some of it here. And with that, I'll stop and answer any questions.
Thank you, Bob. Congratulations on pulling this all together. I know it's been a labor of love. So the top question I anticipated: how can CEDAR community members request HARP experiments?
Well, stand by. We don't know exactly yet. We'll put up a website. We're trying to, like I said, learn from Arecibo. We'll have something like Arecibo. There'll be a website you can apply for time. And also, please write proposals to NSF to support your time. And then the HARP Advisory Committee will allocate the hours. We're planning for at least a couple hundred hours per year experiment time for NSF investigators.
All right, and a second one that probably goes to the heart of our community in terms of planning, even for the decadal survey: is there any plans to add a diagnostic incoherent scatter radar at Gakona?
Yeah, there's a strong desire to do it. They're not cheap.
Yeah.
The MUIR has some capability. It's not an ISR, but we've had a lot of discussions over the years, and I know that AFRL is developing a new modular ISR. HARP can do very exquisite, very detailed things, and with some of the stuff we have, ionosons and other things, the science is good, but we could sure use an ISR there. So if anybody has an idea how to get funding or how to get one there, that would be a super matchup. All
right. Can you say more about PARS? Is it a program or a working group? What's its organization?
It's a summer school. We're putting it back in place. We'll have a leader who will be leading it, setting out advertisements, and hopefully we have some funding to carry out the program, and hopefully by next summer, maybe in August of next year, we'll have probably 2-week PARS summer school in Alaska.
All right. I want to come, but I'll bring my mosquito repellent.
Sure.
All right. This concludes the plenary session this morning. I have just 3 announcements that I know are eating into your coffee break, so I'll make them short. First off, this has been an extraordinary effort to have an online and very professionally run meeting. So I would like to take a moment to thank from UCAR Multimedia. Kevin Taveras, Paul Martinez, and Reed Summer. You probably have seen their faces occasionally. You've heard their voices more often, but I can't tell you enough how important it is to have these people with their kind of calming voices in the background saying every time some little glitch comes up, no worries, we'll take care of it. So just a huge thank you to that team. It has run so much better than I could have hoped, and we got a thank you from Reed and his group. Also, there has been, as you know, a multi-month effort. It's actually year-round that goes into putting this meeting on, headed by a lot of organization within the CEDAR steering committee. But when it comes right down to the daily implementation, you've seen the emails from Astrid Mata, from Michelle McCambridge, Heidi Allen, and occasional extra hands-on from Kendra Grab. And thank you so much to this team. The emails that have flown even throughout the meeting, but every night afterwards to make sure that we're all lined up for the next day. This is such a professional group. I know that you've seen a number of these people at the meetings in person, but again, just a huge thanks to all of the folks who have been backing me up. We just could not put this meeting on without you. So again, thank you so very much. And I don't know, Reed, can we actually see the faces? Do Michelle and Heidi want to come out of hiding and show themselves?
Sure, we can all open our mics and
okay, and Astrid, of course. All right. Thank you so very much. What an incredible team to have backing up. And now for a couple of public service announcements. I am asking for public service. The CEDAR Science Steering Committee is going to draw down just a shade with a number of people rotating off, including me. And so we still need the volunteers to keep everything going and running, hopefully for a meeting coming up in person in the following year. So please do nominate your colleagues who you know have leadership capabilities or who want to test them out. And you can nominate yourself. We've gotten a few nominations over the week, but I know Larissa would really appreciate having these names in the queue so that we can start considering them at the next CEDAR Steering Committee meeting, which is coming up in a couple of weeks. And thank you to the students. The students did an amazing job on Sunday. They are putting me to shame by publishing a regular, although yearly, student newsletter. I hope when I roll off of this this very active role and just send emails to torture the CSSC, that one of the things that we'll be able to do is maybe revive some of the CEDAR newsletters so that we have an opportunity to more regularly highlight the science that's coming out of this very vibrant community, much more so than just the yearly meetings. So you'll probably be hearing more on that. There is funding for CPAS, which is the organization that holds the grant holds the award for this meeting, to do more work in terms of updating the wiki page and maybe making it not a wiki page, but something much more interactive. So stay tuned for that. And Astrid, is there anything I have forgotten to say that I should say before we go off to coffee break and then come back for the remaining workshops?
No.
All right.
Everything's set.
All right. So 20 minutes, please, for return to workshops, and I'm going to jump into workshop mode. And here come the lists for what's going on in the next several hours. Thank you.